my 60 minutes. So that means I got to be done at about 9:45. So I've got a lot to cover. I think I just heard another beep or something. Did someone else raise their hand? Maybe, oh, I bet you it's the recording part, sorry. It's the recording part. Okay, so here we go. There are 4 objectives today, okay? This is section 8.8, it's on power series. We want to be able to understand the definition of a power series, find the radius and interval of convergence, determine the endpoint convergence, and differentiate and integrate power series. So I'm going to try to hit all 4 of those things today and try to hit those in some detail. By the way, this little picture down here, that is those are Taylor polynomials, and as you can see, as we increase the number of differentiations that we're doing when we build these Taylor polynomials, it's getting more and more like the curve that we're trying to get, which, does anybody recognize that curve? Oops. It is the cosine curve. That is exactly what it is. All right, so here is our first most important slide. This is basically the definition, almost, not quite the general definition. This is, if you will, like the Maclaurin power series, because it's centered at 0, and you can probably tell that it's centered at 0 because of this. So a power series is in this form. It is the summation from n equals 0, notice it says 0, to infinity of c sub n x to the n. So the first term would be c0, then it'd be c1 times x, and then c2 times x squared, etc. Where x is the variable and the c sub n's are constants called coefficients of the series. Oh, I guess I should stop right here. What makes this different than what we talked about last week? Well, the key word is series. And what is a series in general? Well, it's a concatenated form of the words infinite series. So last week we were talking about a finite number of terms. How many terms are we talking about now? Infinitely many. So you technically, this is the only way you can write an infinite series. This is, obviously we have to do those ellipses there, the ellipses there, that tells us that goes on forever. For each fixed x, so once we pick what x is, the series 1 is a series of constants that we can test for convergence or divergence, and that's what you're going to have to do on a lot of the problems on this week's homework. A power series may converge for some values of x, and it may diverge for other values of x. That's going to be important for us to investigate. The sum of this series is a function that looks something like this. In other words, we can use a power series to represent functions, and that's exactly why we do that. The domain is the set of all x for which the series converges. Guys, if the series doesn't converge, it's not defined. It's going to infinity, which is going to not be very useful to us. Notice that f represents or resembles a polynomial. That's exactly what it is. It's an infinite number of terms polynomial. The only difference is that, and that's what it says there, f is an infinite number of terms. For instance, if we take Cn to equal 1, in other words, all the c's are 1s, then this geometric power series is 1 plus x squared all the way through x to the n, dot, dot, dot. This particular power series will converge on this interval of convergence, and it will diverge everywhere else. Now notice the endpoints are not included here. That's something else we're going to have to talk about. That was our third objective for today. In fact, if we put 1/2 into this particular geometric series, and by the way, remember, we just said that it converges when it's less than 1 and greater than -1. 1/2 falls into that category. This is, and by the way, that should look familiar. Does anybody recognize that? Well, it's a geometric series, right? And what's the R value here? 1/2, which is less than 1. So this is clearly going to converge very easy, quick for us to know that. We don't even have to try to figure out what the sum is. But we can actually find this. By the way, how would we find the sum? I should probably mention that. How would we find the sum of this? What's the formula? You guys remember this? Okay, we're going to use that later today. So, if we put x equals 2 in, not 1/2, by the way, 2 is not in that interval of convergence, we can clearly see that we get this series right here that is divergent. It's clearly going to grow without bound. So as we can see, this geometric series has values of x for which it converges, and it has values of x which it diverges. More generally, a series of this one, now we're kind of almost, if you want to think about this, is kind of like the Taylor, you know, and we're going to talk, there's a section on Taylor series, we'll talk about that later. This is more like Taylor. So this center does not have to be at 0. So you'll see now, the only difference between this slide and the one from earlier is instead of it being x and x squared and x to the third, is it's x minus a, then x minus a squared, etc. This is the general form for a power series. We're talking about the power series. Hopefully you understand why it might be called a power series. Think about what the power rule is in calculus. We would say that this is a power series in x minus a, or a power series centered at a, or a power series about a. Notice that in writing out the terms corresponding to n equals 0 in equation 1 and 3, we've adopted the convention that x minus a to the 0 is 1, even when x is equal to a. Notice also that when x is equal to a, all of the terms are 0. So if you let's say that a was 3, and then you wanted to figure out that it was centered at 3, then you're going to have 3 minus 3, and all of the terms will be 0. Well, this is an interesting phenomenon because that tells us something we'll talk about later. So let's go ahead and look for what values of x is this series convergent. So here's our first example. I'm going to put my clicker down. All right, so in order for us to figure out where this guy converges, we are going to use one of our favorite tests, or one of my favorite tests. We'll use the ratio test. Ratio test. In other words, we're going to look at the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Hopefully you're familiar with that. That's what you have a test on tomorrow. In other words, this is going to be the limit as n goes to infinity of, and then so this is going to be n plus 1 factorial x to the n plus 1 divided by n factorial times x to the n. Technically, we're doing absolute value here, but we don't need to really worry about that so much. Well, except for maybe the x. We do need to worry about with the x. But the n is obviously going to be greater than 0, so we're good with that. Okay, so let's do a little bit of work here. So we've got a limit as n goes to infinity, absolute value of n plus 1 times n factorial. That's that little trick we've used frequently in this chapter. So that n plus 1 factorial is the same thing as the quantity n plus 1 times n factorial. Similarly, we can break this into x to the n times x to the first, if you will, divided by n factorial over x to the n. I'll put a little dot there. Now I'm writing things conveniently so that you can see what's going to cancel. In fact, let's just go ahead and do it. The limit as n goes to infinity. And now we're going to mark out, well, let's see here, n factorial and n factorial cancels. X to the n and x to the n cancels. So that leaves us with the following. The n plus 1 times x. So now my question is when is the ratio test true? Or, let me say this. When does the ratio test tell us we have some convergence? When it's that is positive and finite, right? Or is it less than 1?
Is it less than 1?
I don't know.
I don't think so.
So guys, here's my question for you. Is the ratio test true for when the limit is less than 1? Or is it just that it's positive and finite? I'm asking you the question.
I think it's just positive and finite, because either way.
Okay, well, you said less than 1 at first, so
Yes.
I'm asking you guys. Does anyone in virtual land want to just type something in the chat, maybe more than one person, just so we can get some clarification?
I heard one comment.
Did someone raise their hand? Just type it in the chat, guys.
Right? Yeah.
Or unmute yourself.
Tom Fenton might answer. A second.
Okay, Gavin said not equal to 1. Has to be less than 1, Rich says, okay. All right, so, but here's my comment to this. What is this limit?
Infinity.
It's infinity.
So it doesn't matter.
It doesn't even matter in this example.
Yeah.
Okay. So in this particular example, this limit is infinity. Right? So I'm going to tell you that this, let's see here, I'm going to call it power series. This power series diverges for all x. Except what? Please type your answer in the chat if you know the answer. Don't say it out loud. Type it in the
I'm
chat.
totally wrong.
Shh, don't say it. Type it in the chat. Just hold your thoughts. Okay, I won't give everyone a chance. I wrote that this power series diverges for all x except. There you go, Gavin. That's exactly right. So earlier, in fact, let me go back to when I made that comment. I think it was right here. Earlier, I made this comment, the previous slide actually. I said that if our center was at 3, oops, I wrote that incorrectly. That should be x. If our center was at 3 and x was also at 3, you'll have 3 minus 3. In fact, if we look at this example here, if we set x is equal to 0, what are all the terms going to be? 0. And what's 0 plus a 0 plus a 0 infinitely many times? It's 0. This is an important fact. I should probably circle this whole thing. So for what values of x does this series converge? Only x equals 0. That's actually the best answer. In fact, let me just go ahead and let you know one of the key points of power series. A power series will always at least converge at its center. Always. 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 So if I ever give you a power series, there's always at least one value of x that it has to converge. Okay? And we'll see. You don't have to write that down. I'm going to come back to that in a slide later on. Does that kind of make sense, though?
Not the same.
Okay. Say it again.
If it doesn't have the same.
Then it's not a power series. Okay. Power series. Next slide. We will see that the main use of a power series is that it provides a way for us to represent some important functions that arise in mathematics. In fact, I want to mention one here in just a second. I don't know that you guys will be familiar with it. It's called the Basel function. If you are a number file follower, you may be familiar with it. In particular, the sum of the power series, and this is j naught of x, is equal to the sum n equals 0 to infinity. We can see that it's alternating here. It's -1 to the n, x to the 2n, so that means even powers of x, over 2 to the 2n, so we're talking about even powers of 2, over n factorial squared. This is called the basal function. It's a very famous function. I believe, and don't quote me on this, guys, I think you guys have heard me mention this guy's name before, Euler. In fact, yeah, you absolutely have to, because that's one of the things we did in this class. I think Euler is the one that first worked on this. Maybe he wasn't the first one, but he found a lot of results from this. So a couple of things that I could mention here that come up in the real world about the basal function are acoustical radiation. That is. How about dynamics of floating bodies? That sounds like maybe a physics thing. How about probability density functions? Is anybody in AP stats in here by chance? Have they mentioned probability density functions? Okay, so probability density functions, in fact, there's literally a whole school of mathematics called this, School of Statistics at most universities. Like at IUPUI, I had a couple of choices, if I can say it. I could have went into the statistics program. I could have went into the pure math program, or I could go into the education program. So there's a whole branch, and it's actually a very lucrative branch to be in, because a lot of people pay big money for you to be able to tell them, what are the statistics of stuff going on in their company or in their world. We know that the sum of this series is equal to the sequence of partial sums. So when we define the basal function as the sum of the series, we mean that for every real number x, j naught of x will equal the limit as n goes to infinity of the partial sums of x, where the sum is defined as follows. Here are for a few of those first partial sums. So this is actually very similar to our I think the warm-up. Didn't we have that for our warm-up for the first one? So there's the first partial sum. The second partial sum, it's not too bad. Then here's the second, and then the third. Now, I'm not going to go through all these, but you can see that, first of all, it's alternating. I mentioned that it was alternating. I told you that the x's were even powers, which they are. And then on the bottom, you have that n factorial. I think there was a 2 to the 2n, and then I think that this was squared. So you'll notice that the bottom has powers of 2 that are even times n factorial squared. Here's the graph of the basal function. Here's some of those partial sums. So here's S naught, that's just 1. And then if we keep adding more and more terms, and if you want to think of these kind of as, like last week when we talked about the, Maclaurin polynomials, we get this. Now here's a more accurate graph of the basal function. Pretty interesting graph. For the power series that we looked at so far, the set of values of x from which the series is convergent always has turned out to be an interval. All right. Important theorem right here. Important theorem. We already talked about the definition of a power series. Oh, and I got to make sure. I think I have a poll question for you guys. Okay, here is your first poll. I already did example 1, correct? Okay, there's your first poll question. This is a tough one, so be careful. All right, so for the following theorem, it says, this is true. For a given power series, the sum from n equals 0 to infinity of some constant c sub n, x minus a to the nth, there are only 3 possibilities. 1, I've already mentioned this one, the series has to converge in the case at its center, basically, which we've already mentioned. In fact, the first example was based on that. 2, the other option is that it could converge for all x's. In other words, it could converge for all real numbers. In other words, any x you put in there. By the way, these are my favorites, because then you don't have to worry about the x. It works for any x you want. And then 3, and this is the one that you're going to probably spend the most time dealing with, unfortunately for you, because this one requires quite a bit of work. Case 3, there is a positive number r that's called the radius of convergence. This r is referred to as the radius of convergence. such that if the series converges, we're going to get the absolute value of x minus a is less than r, and it will diverge when it's when it's greater than r.
I wonder which one we're gonna be working with tonight.
Yeah. Well, this one's an easy one, right? We've already seen an example. This one's my favorite because it just, I like it when it works always. But there are times that we're going to use this. Now, the reason, in fact, before I do any more examples, the reason that this is important is, guys, if the power series does not converge for that particular value of x, then there's no sense in looking at it, right? So we need to make sure we understand that. The interval of convergence of a power series is the interval that consists of all the values of x for which the series converges. In case 1, it's just going to converge at a single point, which I just asked you a whole question about. Case 2, well, the interval of convergence is everything, so that's easy. It's negative infinity to infinity. Case 3, note that the inequality, the absolute value of x minus a less than r, can be rewritten as negative r less than x less than a plus r. Now, here's where we're going to be a little bit careful. We have to worry about the endpoints. This is our third objective. So I've just mentioned the radius of convergence and the interval of convergence. We also have to be concerned with the endpoints. What I mean by that is, in fact, do me a favor, ignore these 4 possibilities here. Just look at this graph right here. Now, we're only talking about case 3 right now. When it's a finite number of, I shouldn't say finite, that's incorrect. When it is a interval of convergence that's not infinity, and it's not just the center. You could have, by the way, the rate, let's just make this up. Let's just say that the radius of convergence here is 1, just to keep it simple. And let's just say that a here is equal to 0. So let's say that this is 1, and this is negative 1. So let's not get too general yet. Let's just pretend that we're talking about a power series with a center of 0 and a radius of convergence of 1, right? So that means as long as we pick values that are less than 1 and greater than negative 1, kind of like the one we did earlier today, everything's good. If it's outside of that, it's bad. It diverges. There are 4 possibilities, though, in this particular situation. Let's go through them. Case 1, it could be that that power series diverges at both negative 1 and 1. In other words, you would have an open, notice this is open, set of parentheses. So in other words, it would be negative 1 to 1, excluding the negative 1 and 1. Or you could have it to where this endpoint is convergent, but this one is not, so then you have an open. Of course, you could have it the other way around, where this point is closed and this point is open, and then of course you could have it where both endpoints are closed. I hope you are catching on that what I'm telling you is that these can be quite a bit of work to analyze. Because not only do you have to figure out what the radius of convergence and the interval of convergence is you will have to test the endpoints. And on the AP exam, this is typically like a free response type of question. And you know they're going to give you a point or 2 for those endpoints. So let's go ahead and look at an example here. Again, which test do we want to use here? We're going to use the ratio test. The first thing we're going to do is we're going to use the ratio test. Remember, the ratio test is the limit as n goes to infinity. Absolute value of a sub n plus 1 over a sub n. And what do we want that to be? Yeah. Like, what do we want that to be? What do we want that limit to be? You said it earlier. Okay, now I've got it totally unconfident.
What? Less than 1.
Less than
Oh,
1, thank you. Okay. We want that to be less than 1, right? If it's 1, remember when we did the ratio test, we said it was inconclusive, right? So that's what we want. So let's go ahead and look at that here. And by the way, can we just kind of skip the point of this alternator? Since we're doing absolute value, all the alternators are going to become positive, right? So we're basically, if we're going to look at this, I'm just going to be doing n 4 to the n, and then I guess I could write this on the top, x minus 5 to the n on the top. Say it again. They have to start at, do you understand why that started at 1 here? Nope. Look at the denominator. You see the n in the denominator? If this was 0, then that would be undefined. So, yeah. So we can't do it at 1 on this particular example. Okay, so let's go ahead and deal with this guy. So we're going to do limit as n goes to infinity. And I'm just going to go ahead and, if you guys don't mind, I'm going to go ahead and multiply by the reciprocal instead of writing a big fat, or not big fat, big tall division. So we got to do the x minus 5 to the n plus 1 over n plus 1, and then 4 to the n plus 1 in the denominator, times, now I'm going to flip that other guy over and make it just the nth one, x minus 5 to the n. Make sure I got that right. Okay, good. Now, guys, again, please note, I am disregarding that negative 1 to the n because the absolute value is going to kill it. Okay. All right, so now we got to clean this up a little bit. All right, so we're going to play the same game we've been playing. In fact, we played this game just a few minutes ago with the last one. I'm just rewriting this a little bit so that it'll hopefully show us what things are going to cancel here. So then I'm going to pull this denominator piece over here from the right over to the left. And then I'm going to have this, I'm going to rewrite this here. Let's see here. I'm going to put, did I skip something here? No, I'm okay. This right here, now I'm going to deal with that 4 to the n plus 1. That's going to be 4 to the n, and then I'm going to put times 4 there. There's still this n plus 1 on the denominator. So I'm just kind of changing the order of the denominator there. Hopefully you can see what I did. The only thing that really changed was I changed that 4 to the n plus 1 to 4 times 4 to the n. Does that make sense? Okay. Now, hopefully I've written this in such a way that it's easy to see what cancels. I hope. So that's going to cancel that, and this is going to cancel this. So things are already looking quite a bit better. So we are going to get the following. We're going to get the limit, and n goes to infinity. And I think I'm going to put the n stuff first is what I want to do. Yeah. So then we're going to have, there's an n in the numerator, and then an n plus 1 in the denominator. And there's a 4 as well, so maybe I'll pull that 4 out. I think that's what I did with, yep, pull the 4 out there. And then I'm going to multiply this by the absolute value of x minus 5. Now, guys, I'm kind of assuming do you guys understand what the limit of n over n plus 1 would be? It's just 1. Does everyone understand why it's 1? Do I have to go through and explain why that's 1? I'm asking this question, guys. Let me know if I need to explain this. You guys understand that that's 1, right?
Yeah.
Okay. We've done that way back in Calc 1, but I just want to make sure. I'm going to kind of skip over that just to save myself some room. In other words, what I'm telling you is that this is going to be 1/4 absolute value of x minus 5, and we want that to be less than 0, correct? Oh, I'm sorry, not less than 0, less than 1, right, Jack? Yeah. We're going to put that on here. Less than 1. And now, this is the big thing right here. Hopefully you'll understand where this comes from. This is the key observation right there. You understand if we multiply 4 on both sides, that 1 becomes 4, right? This gives us what we need to know, which we already kind of knew at the get-go, I think. Didn't we kind of already know that our center was at 5? If we look up the original problem. And now guess what we have? What's that? That's your radius of convergence. Right? So I'm going to come back to this slide, but let me go back to this slide right here. You see this, the bottom? It says the absolute value of x minus a greater than r. Oops, did I screw something up on my, oh, that was for divergence, wasn't it? Sorry, we want to look at this one. This is divergence. We don't want one in divergence, we want one in convergence. So now we know we've got our center still at 5. We know it's going to converge as long as the radius is 4 or less. In other words, let me draw a little bit of a picture here. Where's the center at? Well, it's 5. If we go forward to the left of that, that's going to bring us over here to positive 1. And forward to the right here, that's going to take us to 9. I'm telling you right now, anything in here or anything over there is good. This particular power series converges as long as we are less than 4 away from the center of 5. Does that make sense? So let me go ahead and maybe write this down. The radius of convergence is 4. Does everyone understand why the radius of convergence is 4? It's because of this. We already knew that it was centered at 5, so that's not very interesting. And in fact, let me just say 5, so x is equal to 5. That's the center. X is equal to 5. Now, we've done a lot of work here. Guess what the unfortunate thing is? We are not done. Guess what we have to do now? We have to test the endpoints. Okay, I'm going to go to a new slide. Does anyone need me to stop before I go on to this next piece? Okay, I'm going to go to the next slide. Okay, good. That's so great that I did that. All right, so I'm going to go back to this. Remember, we are looking at, let me draw the picture again. Here's our center. Here's 1. Here's 9. Our radius was 4, right? So we have the following possibilities. The answer could be 1 to 9. The answer could be 1 to, could be 1 to 9. The answer could be 1 to 9 this way, or the answer could be 1 to 9 this way. Oh boy. We got to check. We just got to check these ones. So let's check. So I'm going to do 2 checks here, all right? So here's number 1. I'm going to check, let's just do the left side. So that's going to be x equals 1. Let's check x equals 1. Okay. If x is 1, that means that this is going to become the following. It's going to become the sum. N goes from 1 to infinity of -1 to the n over n4 to the n times, would that be -1?
4. 1 minus 5.
You're right. Correct. Okay, so let's play with that. N equals 1 to infinity of -1 to the n over n4 to the n. And then I'll write it like this. N. How about that?
All right.
Will that work? So far, so good? Okay, so let me make a couple little notes here. What's going to happen to this and this?
Good.
Cancel. What happens to these two guys? What's negative 1 to the n times negative 1 to the n? Well, that'd be negative 1 to the 2n. Would you guys agree with that? Which is what? 1.
Yeah.
In other words, this whole thing becomes the sum from n equals 1 to infinity of 1 guess what that is? That is our most famous series, the harmonic series, which is divergent. Harmonic series is divergent. That means that we cannot include 1. In other words, I'm telling you, the answer cannot be that, and the answer cannot be that. About another slide here or not? I think I know. Okay, I've got to squeeze all this in into this one. Okay, I'm going to have to squeeze it in over here. Okay, I'm going to try to do it down here. All right, so now we need to check. So here's number 2. We got to check x equals 9. What are we doing on top here? Oh boy, I got to finish up here. I think we're getting close to the end though, aren't we? I got to do one more with some calculus. Okay, I'm going to go faster here. So now we're going to do the exact same thing. Now I'm going to plug in 9. And what's 9 minus 5? 4. Okay, so this is going to be the sum, n equals 1 to infinity of negative 1 to the n over n 4 to the n times 4 to the n. Agreed? Guess what happens to the 4 to the n and the 4 to the n? Cancel. So you are left with the following. The summation. Biggest pet peeve is does that. N equals 1 to infinity of negative 1 to the n over n. Oh, guess what that is? This is our alternating harmonic series, which we know does what? Converges. Therefore, the power series interval of convergence is 1 to 9, including 9. In other words, what I'm trying to tell you is if I have figured out that this power series is, somehow useful to me, as long as my numbers are in this interval, we're good to go. So for example, if I wanted to figure out, can I use this for 8, x equals 8? The answer is yes. Can I use it for 8.327?
Sure.
Yes. Can I use it for 9?
Sure.
Can I use it for negative 1? No. Can I use it for 1? Can I use it for 0? Does that make sense? This power series is fine and wonderful as long as it's in that interval of convergence. Does that make sense? By the way, do you understand why we did section 8.2, 8.3, 8.4, 8.5, 8.6? Yeah. If you don't know the convergence tests, then you don't know when this thing can be used and when it cannot be. You guys have taken a big step today. Today we are now looking at infinite series to deal with functions. All right, guys, I am running long here. I'm technically at the last minute here. Here's the last thing I'm going to say very quickly, and I'm going to do the last example. If you need to break off at this point, you are allowed to. I'm not going to make you stay, but I do want to try to get this last example in, and then I'll stop recording. But again, if you need to go because you have a test today or something else, you're not going to hurt my feelings. Theorem 821, properties of functions defined by power series. Here's what I want you to notice. Guess what we can do to power series? Calculus. In other words, I can do, if I know this is my power series, I can do the derivative of it. In fact, what's the exponent here? It's 9, correct? So if I want to do the derivative of it, well, you subtract 1 from the exponent and then you multiply the n in the front. Similarly, but in the other way, we can also integrate power series. Now notice when you integrate, what you do the exponent. You add one. Notice that I added one, but then you also have to divide by that amount. That's why they're called power series. Do you remember our power rules for differentiation and integration? They come back to play here, which is nice. Okay, here's my last example, and I'm going to go very quickly. It says prove that for -1 less than x less than 1, that 1 over 1 minus quantity x squared is equal to the following. So I'm going to go back to something I mentioned earlier. You guys don't remember this? This was the geometric series. I mentioned that earlier. This particular geometric series is equivalent to 1 plus x squared plus x to the third plus da da da. Okay, we looked at this before, right? And by the way, we already know that it's, I guess maybe we don't know that. I'm going to tell you that the radius of convergence there is 1. But here's the interesting observation. What is the derivative of 1 over, what is the derivative of 1 over 1 minus x? Let's look at it, okay? So what would that be? So we could use the quotient rule if we wanted to, right? Or we could do the following. We could do our power rule, right? So what is that going to be? We'd bring the negative down. We would leave that alone. That would become -2. Oops, and then I almost screwed up the most important part. What do we have to multiply by? The derivative of the inside, correct? What is the derivative of the inside? Well, 1 minus x's derivative is -1. Look what happens to the -1 times the -1. What do you get? Well, this derivative turns out to be 1 over 1 minus x squared. Oh. Do you guys see a connection there? I am starting with something that we are familiar with. We've already looked at that. You looked at it in the last section. Now what I'm telling you is the derivative of 1 over 1 minus x is going to give us 1 over 1 minus x squared. Oh, I think I have a typo here. No, I didn't. I'm good. I'm good. I'm sorry. I just thought I screwed that up. I'm good. In other words, what we can do is now we can take this and do the derivative of it. 1 plus x squared plus x to the third plus da da da. We can do the derivative of this. I'm doing the derivative of this because I know the derivative of this is this. So I can do the derivative of this. Well, that's easy. What's the derivative of 1? 0. What's the derivative of x? 1. What's the derivative of x squared? 2. What's the derivative of x to the third? 2. Does that look familiar?
Yeah.
Okay, so that's all I wanted to get in. This definitely takes some practice. I know that wasn't difficult, but you have to recognize that. By the way, I am throwing out, in case you were not sure where this whole thing came from, you're going to spend more time with it next week as well. On the very last slide, I've got a summary of our radius of convergence and common power series, but I'm going to stop there because I'm now 5 minutes over, and I am super sorry to say that. So I'm going to stop recording. We are done with section 8.8.